All right, here we go with equilibrium and equilibrium constants. So equilibrium is a condition in a reaction that actually exists for a great number of processes that you may not be familiar with. But we're just going to launch straight in and see where we go. All right, so we're going to link to equilibrium from kinetics. So kinetics is the study of change in conditions as a function of time. And using the integrated rate law, we can calculate the conditions after any period of time. Equilibrium, on the other hand, is the study of the conditions of a reaction or a process after a substantial, we say an infinite amount of time has passed, but certainly after a protracted period of time has passed. So our model from the last chapter, from the kinetics chapter, was a bit off when what we're talking about is equilibrium. Because remember, in kinetics, we're generally talking about the initial rate method. We're talking about how fast the reaction is going initially, and then when it was primarily going in the forward direction. What we discover is that if we run a reaction for a while, that we're starting to build up products, because remember, reactants are disappearing, products are appearing, and so what happens, and you know this from the kinetics chapter, reaction slows down. Well, eventually it actually slows to zero. Now here's the deal. It does not mean that the reaction stops. It just means that the rate of the reaction in the forward direction starts to equal the rate of the reaction in the reverse direction. In other words, what's actually happening is the products begin to produce reactants. And at equilibrium, the forward direction equals the reverse rate of the reaction. So that means that this concentration and this concentration, the concentration of our products, stops changing. It doesn't go to zero. It doesn't go all the way to infinity and these all go to zero. The concentration of our reactants also stops changing. These become constant at equilibrium. All concentrations become constant at equilibrium. Okay? Constant concentrations. It doesn't mean that the reaction has stopped. Remember, the reaction is still going in the forward direction. The reaction now is also going in the reverse direction at the same rate as the reaction is going in the forward direction. And that's why these concentrations stop changing. Nothing's at zero here in an equilibrium reaction. They just stop changing concentration. So the net rate forward and the net rate zero could be considered to be zero, because you're not, the reactant concentration is no longer getting lower, and the product concentration is no longer getting higher. All these concentrations are remaining the same. So we can describe the final concentrations at equilibrium in this way. So let's say I start with 1 molar of nitrogen and 3 molars of hydrogen, and this is the Haber-Bosch process. You've seen it before, and it's just a 3-to-1 ratio for hydrogen to nitrogen. And at equilibrium, after I run the reaction to the point where the concentrations of the products and the reactants stop changing, I wind up with 1.41 molar of ammonia and 0.89 molar of hydrogen and 0.30 molar of nitrogen. These are the equilibrium concentrations, okay, at equilibrium. I'm not losing any more reactants, and my product's concentration is staying the same. Now, if this is the way an equilibrium reaction works, I could also get to the same concentration by approaching the reaction from the reverse direction. That is, if I have the same temperature in the same 1 liter flask and I start with a 2 molar concentration of ammonia, at equilibrium, I'm going to have the same equilibrium concentrations. The reaction simply starts from the reverse process, treating ammonia as a reactant, and this concentration starts to go down, and this concentration and this concentration start to go up. So we wind up with the same equilibrium concentrations. That's the nature of an equilibrium reaction. And we can describe this equilibrium mixture as a ratio of products over reactants. I'm going to show you how to do that. So here's the way we derive the equilibrium constant expression. We allow this reaction to take place, to go on until equilibrium is reached, that is, until all concentration stops changing. That's where the rate forward is equal to the rate reverse. And we can set those rates equal to each other at equilibrium because they are the same rate. And so here is the rate law for the forward direction. All we've done is we've treated this as an elementary reaction based on the molecularity. So the hydrogen we raise to the 3rd power. The nitrogen has a coefficient of 1. We raise it to the 1st power. So this is the rate law. K is K times nitrogen times hydrogen cubed is equal to K prime. This could also be described as K reverse. This could be K forward. This is simply the rate forward is equal to the rate reverse. Okay, and so this is the rate law portion of that. And then we solve for the equilibrium constant expression, and our protocol is to have the products in the numerator. So here's your products raised to their coefficient as powers, divided by the reactants. So here are your reactants, raised to their coefficients as power. This is a 1 here, this is a 3 here. That's the coefficient of hydrogen. And then we've got K forward over K reverse, and we simply denote that as capital K, and this is our equilibrium constant. And this is this expression right here, which is the crux of the matter in this entire chapter. This is the equilibrium constant expression. So you're going to want to remember how to do that. It's products, constant expression. You know my handwriting is terrible. Okay? So listen to my words. It's the equilibrium constant expression. And you're going to want to remember how to write an equilibrium constant expression based on an equilibrium reaction. Just to emphasize once more, we get the equilibrium constant expression, which is just products over reactants from we're treating this. You've got nitrogen, N2 plus 3 H2s over here on the reactant side. The reaction spontaneously begins to make products, and at equilibrium, these concentrations stop changing. And just setting the rate laws for the forward and the reverse direction equal to each other, we can derive the equilibrium constant expression. You need to remember it. Products over reactants. That's the way that that works. Okay? We could also reach the equilibrium by starting over here with NH3. We got two of them. Run the reaction in the reverse direction, and we can reach the same equilibrium constant expression under the same conditions. All right, that's the nature of equilibrium. All right, so just the formalism of it. The lowercase letters are the coefficients, and the reactants and products are the uppercase letters, the capitals, all right? And so the equilibrium constant expression, the K sub C here just stands for concentration. It generally means we're doing this in molarity. Honestly, it isn't that important because the equilibrium constant is really just a ratio of products over reactants. That's really the nature of an equilibrium constant expression. And it tells us how far does the reaction go into the product direction, okay? Does it favor the products? Is it a really big equilibrium constant, which would indicate that you had a very large numerator in this expression, and this would be very small. And that would be if you had a really large K. And if it were a really small K, then it would be favoring the reactants. All right? And we'll get to that a little bit later. Don't worry if you didn't quite get that yet. But we'll get there. So all concentrations raised to the power of their coefficients, product concentrations in the numerator, reactant concentrations in the denominator. The subscript C in this case just indicates the constant applies to concentrations instead of pressures. I can do equilibrium constant expressions in concentrations. I can do it in pressures using those as concentrations. I could do it as a mixture of pressures and concentrations. Remember, this is a ratio of products over reactants. So here we go. Determine the equilibrium constant for the following reaction. Here's our equilibrium reaction. I'm going to make sure, and if you haven't noticed it before, let me make sure that you get it. The equilibrium reaction is denoted, generally the forward direction is on top and the reverse directions on bottom. I've reversed that, but don't worry about that. These are the equilibrium arrows, okay? It's not a double-headed arrow. It's one arrow going forward and one arrow going in reverse, all right? So if I want to write the equilibrium constant expression, remember it's products over reactants, and here are your reactants. We're going to raise each product to its coefficient as a power, and we're going to raise each of the individual reactants to their coefficients as a power. So I'll leave it to you to solve that particular problem. Should be pretty easy. Okay. Working with gases, we would just call this K sub P. And again, I don't make a big distinction between K sub P and K sub C. They may be different because pressures are not concentrations, but they represent concentrations. It's still products. It's still products raised to their coefficients divided by reactants raised to their coefficients as powers. Okay? And we can convert between K sub C and K sub P. All right, and this is the equation that we would do this with. K sub P, the equilibrium constant for gases, is equal to K sub C times the gas constant, RT, and that's the one from the ideal gas law, 0.0821 liter atmospheres over moles Kelvin, times the Kelvin temperature. Remember, anytime you're working with gases. You've got to be in Kelvin. And the delta N is just the number of products minus the sum of the number of reactants. So if I had N sub 2 plus 3H2, and that is an equilibrium reaction making 2NH3. And this is a gas phase reaction. And I want to figure out what delta N is. This is going to be my 2 moles of ammonia. So that would be 2. These are my products. And that's going to be minus the sum of the coefficients of my reactants. That's 3 plus 1, so that's 3 plus 1, so that's 2 minus 4, which is going to give me a minus 2. So this would equal delta N in this expression, okay? You need to be able to manipulate this expression. If I were solving for K sub C, all I would have to do to solve for K sub C, okay, is isolate it, which would mean I would divide both sides by RT times delta N. So if I were solving for K sub C, that would just be K sub C is equal to K sub P, that's K sub P divided by RT raised to the power of delta N, okay? So it's just a little bit of algebra. You can handle that. Last thing we're going to do on this little video is calculate the equilibrium constant for this reaction. Okay, so let's calculate the equilibrium constant given that our equilibrium concentrations for the Haber-Bosch process, 1.41 molar of ammonia, 0.89 molar for hydrogen, and 0.30 molar for nitrogen. So here we go. So we're just going to go ahead and do this. This is going to be, and I recommend usually that the thing to do is go ahead and write what you intend to do symbolically before you start plugging in numbers. And that is the easiest way to avoid messing up. All right, so now we can plug in our values. That'll just be 1.41. That's going to be squared because the coefficient of ammonia is 2. If I can get it to stay there. For nitrogen, it's 0.30 to the first power times hydrogen, which is 0.89 to the third power cubed. And then make sure that if you're going to do this all in your calculator, that you put everything in the denominator in parentheses. And if I do that, I get 9.4, and that is my equilibrium constant. Okay? All right.